radius over j. Now j, there's no j x-axis of j y over here because it's a shaft. Shaft j is the second polar moment of area. Now we also know this relationship, right? So now I'm going to substitute everything into the above, or I'm not going to substitute. I'm just going to still write out this formula of stress M. Okay, so this will be equal to, I'm going to write down shear max is equal to M. I'm not going to break it down into components. Okay, so M multiplied by the radius, right? Because Z and X or Y and Z in a shaft is also equal to radius, right? Okay, so that's why I put MR over 2I, because it's half, right? Squared plus by TR over J, and this thing is also squared. And I want to write down here, note that J is equal to 2I, right? So we know that I, second moment of area, for a shaft okay, so either it is IYY or IZZ, does not really matter. It's equal to pi R4 over 2. Okay. And for J, which is equal to twice over 4, I wrote out over 2. So this is twice of I, so this is equal to pi R4 over 2. Okay. So we can replace the 2I with J now, right? So the tau max is equal to M R over 2I squared plus by TR over J. Sorry, the 2I you can replace with what? J. Right, so this value over here is also equal to J. Okay. Then we move things around, right? So the common term is the radius and J. Oh, let me use a different color. These are the common terms over here. These are the common terms over here. We're going to take it out, right? So tau max is equal to R over J, right? And then you square root M squared, right? Plus by T squared. Okay. So we're going to focus on to determine the radius of the shaft. Okay, so in general, a formula like this, a relationship like this, okay, we generally over here, right, that I've highlighted, is used to determine minimum diameter of the shaft. Okay. That is the purpose. Okay. So from here, we want to find what is our, in general, we want to find what is our R. Okay. So we rearrange the equation. So J over R is equal to, not stress, yeah, J over R is equal to M squared plus by T squared over tau max. And knowing the formula for J, right? So pi R4 over 2R is equal to M squared plus by T squared over tau max, right? So I'm going to write the formula. I'm going to continue on the same page so it's easier to follow. Right, so you can cancel the radiuses. Not cancel the radiuses. Come on, J. So this will become 3. So pi or R is equal to 2 over pi, right, square root of M squared plus by torque squared divided by maximum stress, right? And this is powered by 1/3. Okay. And then we have to write note right? We will write note that M, right? So M is a resulting moment vector is equal to my squared plus by, or my, or M squared is equal to my squared plus by mz squared. Okay. So the radius down here is equal to 2 over pi. Okay. My squared plus by mz squared plus by torque squared, or in the x direction, and then this whole thing divided by tau max. Now, the bottom tau max over here, right? This is tau max over here is also equal to the tau allowable, which is from material testing. Okay. So with this formula over here, we can determine what? We can determine the minimum allowable radius of the shaft. Okay. Now, the complexity of or this shaft design, as you can see, is controlled by this value, okay, which is your my squared plus by mz squared plus by tx squared. Why this is important? So the location of the element, right? The location of the element or point of interest is dependent on the location where square root my squared plus by mz squared plus by t x squared. Okay, maximum is located. Okay, so we have to take the square of the moment and the top and the whole thing square root, and we have to determine where is this location based on its maximum amplitude. Okay, so we did not do this in the past lecture. We usually tell you, okay, this is element. So if you look at the past examples, right? If you look at the past examples, hold on, not here. If we look at the past examples, or when we were doing compound loading, right? When we're doing, where is compound loading? Not here. Oh, that's week 8. When we were doing compound loading, right? We always give you determine point A and determine point B, right? So for the shaft design, right, we have to find where is the location or point of interest. Okay, it's dependent on where the square or yeah, the square root of the moment and the torque, square root of the whole thing, the maximum is located. That is where the point of interest. Okay, so this is something new. Okay, so now let me introduce. So I think that is enough theory for the day. Okay, we are going to look into the shaft design now. Okay, so this is our example number 1. Let's briefly look at the question first before we go for a break. Okay, so example number 1. Okay, so I post this example on Avenue to Learn. Okay, so let's look at this example. And again, as I said, this is a 3 hours lecture to design transmission shaft. Okay, so I don't think we can get it done today, but we'll try. I'll do as much as we can. So the solid shaft AB rotates at 480 RPM and transmit 35 kilowatt from the motor M to machine 2 connected to gear G and gear H, and 20 kilowatts is taken at gear G, at 10 kilowatt is taken at gear H. Now we are given that the shear stress allowable is 50 megapascal. Determine the minimum diameter of shaft AB. Okay, so what I propose now is we go for a 5 minutes break. And